In 2010, researchers at Zhejiang University did something nobody had thought to do with the most famous structure on Earth. They cooked for it. They prepared lime mortar two ways, the standard recipe and the original Ming Dynasty recipe, which adds one ingredient, glutinous rice boiled into a thick porridge and stirred into the slaking lime. Then they cured both and put both through mechanical testing. The rice mortar came out markedly stronger, denser, tougher, more resistant to water, more resistant to cracking, and bonded to stone so well that in old walls the stone sometimes breaks before the mortar joint does. Under the microscope, the two materials barely looked related. The plain lime cured into loose, coarse crystals, the rice mortar cured into a fine, compact structure, the mineral organized, disciplined, by something threaded invisibly through it. The researchers published the analysis in accounts of chemical research and named the ingredient responsible, amylopectin, the branch starch polymer that makes sticky rice sticky. It was the first molecular explanation for something Chinese builders and conservators had known as lore for centuries, that the old rice mortar walls, tombs, and pagodas of northern China have a strange habit of still standing in a region that produces some of the deadliest earthquakes in human history, while newer repairs crack and fall away beside them. A team of engineers fed the 2010 paper and the seismic history of northern China into Grok AI and asked a simple question: what did the Ming builders actually understand? The answer is not what anyone expected to find in a kitchen ingredient. Here is the mechanism plainly. When glutinous rice porridge is mixed into slaking lime, the amylopectin, a heavily branched natural polymer, disperses through the slurry and inserts itself into the process of crystallization. As the lime cures into calcium carbonate, the starch controls how the crystals grow. It keeps them small, keeps them tightly packed, and leaves an organic network threaded through the finished mineral. The result is not lime with rice in it. It is a composite, the same class of organic-inorganic architecture we met in the last two videos, in Roman concrete and in Maya plaster, tuned this time for a different enemy. Rome's enemy was the sea, the Maya's enemy was the jungle. The Ming builders' enemy was the ground itself and the seismic belt of northern China, which does not push on a wall or rain on a wall, but shakes it hundreds of times a century and demands a material that can take punishment and hold its grip on the stone, dense, tough, tenacious mortar that resists cracking and bonds like a clamp is exactly the answer to that enemy. Think of what modern engineers put under earthquake-resistant buildings, isolation bearings, layered devices designed to soak up violence so the structure above survives. The comparison is loose, and I will keep it loose. But at the scale of a mortar joint, the rice is doing that family of job, making the wall a thing that endures shaking rather than a thing that shatters under it. And one detail tells you this was knowledge, not luck. The builders did not use ordinary rice. They used glutinous rice, nearly pure amylopectin, against roughly 3/4 in the common varieties. Ordinary rice was cheaper and everywhere. Glutinous rice was food for festivals, more valuable, harder to spare, and it is the variety that works. Somebody knew the difference. I'm Dr. James Mercer. Subscribe now and turn on notifications. What I'm about to walk you through has been sitting in the mortar joints of the most famous structure on Earth for 600 years. Let's go back to the beginning. To understand what Grok found, you need to understand what the Great Wall of China actually is, and why survival is the right word for what it has done. The Great Wall is not a single wall. It is a system of walls, watchtowers, garrisons, and signal beacons built over more than 2,000 years by multiple dynasties. The sections most people recognize, the stone-faced walls riding mountain ridges in the photographs, are largely the work of the Ming Dynasty, built between 1368 and 1644. The Ming Wall runs nearly 9,000 kilometers, Count every dynasty's construction, and the system exceeds 21,000. And it runs through one of the most seismically violent regions in Asia. The tectonic systems of northern China have produced catastrophe after catastrophe, including the 1556 Shanxi earthquake, the deadliest in recorded human history, which killed an estimated 830,000 people and leveled ordinary construction across an entire region. That is the ground the Ming built on, ground that periodically tries to shake down everything standing on it. 6 centuries later, the sorting is visible to anyone who walks the wall with open eyes. Original Ming construction with intact rice-lime mortar stands in condition that conservators describe with something close to embarrassment, because beside it stand the repairs of the 20th century made with modern cement, and the repairs are the sections failing, cracking, delaminating from the old stone, letting water in to do its slow work. The newer material is dying faster than the older one. On the same wall, in the same weather, on the same shaking ground, the mortar the Ming used was not a curiosity preserved by luck. It was technically superior to what replaced it, and the reason was not understood and by anyone until 2010. The use of organic additives in old Chinese mortars was never a secret. Historical sources and building tradition describe plant materials in the mortars of important structures going back many centuries, and the sticky rice recipe in particular is documented across a whole family of Chinese construction: city walls, tombs, pagodas, waterworks. The rice in the wall was known. What nobody had characterized was the mechanism. Why rice, and why specifically glutinous rice, rather than the abundant ordinary varieties that any administrator would have preferred to spare? Understand what that specification cost. Glutinous rice was not construction material. It was food, and premium food, in a country where grain was the difference between order and famine. Cooking it into mortar by the cartload for military architecture stretching across provinces was an expensive and deliberate choice that had to be justified up a chain of command. Bureaucracies do not pay premiums for ceremony at that scale. They pay premiums for performance. The grain in the wall is itself the evidence that somebody, somewhere in the Ming engineering establishment, knew the cheap rice did not work as well, because the two varieties look identical in a mortar bucket, and only one of them is nearly pure amylopectin. For most of the 20th century, the scholarly framing of all this was historical and archaeological, not mechanical. The rice was a cultural detail. The idea that the variety selection encoded a material science distinction, amylopectin against amylose, branched polymer against linear, was not a question the field was equipped to ask. The 2010 paper asked it. Grok extended the answer. The team's instruction to Grok: take the 2010 characterization of amylopectin in lime mortar, integrate it with what is documented about the wall's condition and the region's seismic history, and identify what the Ming builders would have had to understand to produce the result that is standing on the ridgelines today. The finding came back in 3 parts. The mechanism at the crystal scale. Amylopectin does to curing lime what the chukum tannins do in Maya plaster. It regulates the mineral. The branched starch binds into the crystallization process and holds the calcium carbonate to a fine, compact, orderly microstructure with an organic network left threaded through the cured mass. Compact crystals mean density. Density means strength and water resistance. The organic thread means toughness, a mortar that yields a little instead of shattering, grips stone instead of releasing it, and closes off the pathways that cracks and water want to take. Every one of those properties is exactly what masonry needs when the ground moves. The variety selection is the technical tell. Grok's comparison of the starch chemistry confirmed what the Ming procurement implies. The performance difference between glutinous and ordinary rice is not marginal, because the working polymer is amylopectin and glutinous rice is essentially all amylopectin. The linear starch that dominates ordinary rice does not build the same network. Whoever wrote glutinous rice into the specification, over the objection of every quartermaster who had to source it, was specifying the correct molecule 7 centuries before anyone could name it. The modern control group. The 20th century repairs on heavily visited sections used modern cement mortar, stronger in a static crush test, and stiffer, more brittle, less forgiving in every way that matters on moving ground. Hard cement repairs on historic masonry are a documented conservation problem worldwide. The rigid, new material cracks, traps moisture against the old fabric, and accelerates the decay it was installed to stop. On the Great Wall, the comparison runs side by side in the same joints, and the old material is winning. The Ming construction is outlasting its own repairs, not because it is older, but because of what is in the mortar. As the team continued pulling the analysis, 3 additional findings emerged. The first revelation: the porridge is the process. The traditional recipe does not call for rice, or rice flour, or rice water. It calls for glutinous rice cooked into a thick porridge and stirred hot into the lime. That detail is load-bearing. Cooking gelatinizes the starch. Between roughly 60 and 80 degrees Celsius, the granules burst and the amylopectin dissolves into a continuous solution that disperses evenly through the slurry. Raw starch would sink, clump, and leave the mortar inconsistent joint to joint. The cooked porridge turns the whole batch into one uniform polymer matrix. It is first-year food science, performed at construction scale centuries before food science existed, encoded as a cooking instruction because that was the vocabulary the tradition had. The recipe is written in kitchen language. The content is process chemistry. The second revelation: the Ming did not invent it, they industrialized it. Rice lime mortar is found in Chinese construction that predates the Ming by centuries, in tombs, in pagodas, in city walls built long before 1368, some of which have themselves ridden out major historical earthquakes. The knowledge existed as craft practice in the building trades of northern China well before the Ming state picked it up. What the Ming contributed was scale, turning a mason's recipe into a logistics operation, grain requisitioned, boiled, and delivered into thousands of kilometers of military construction decade after decade. It is the same pattern as Rome and the ash of Pozzuoli. The state did not discover the material. The state built the supply chain that let the material become an empire's skeleton. The third revelation: the question nobody has run. Northern China's earthquakes did not stop in the Ming Dynasty. The region has been struck repeatedly in the modern era, including the catastrophic Tangshan earthquake of 1976, one of the deadliest of the 20th century, which means somewhere in the structural assessments and conservation surveys of the last decades, there exists the raw material for a study nobody has published. Walk the affected sections, sort the joints by mortar, original rice lime against modern repair, and count what stood and what failed. Grok flagged the question as open. The answer is sitting in survey records and in the wall itself, waiting for someone to ask it formally. If a graduate student in Hebei is watching this, that is a thesis. This is the third video in a sequence, and the pattern across the 3 cases is now clear enough to state directly. Roman concrete, volcanic ash plus lime, producing a self-healing composite through reactive lime chemistry. Maya plaster, Chukum bark extract plus lime, producing a fracture-resistant composite through organic templating of crystal growth, the shell principle, Great Wall mortar, glutinous rice porridge plus lime, producing a dense, tough, stone-gripping composite through starch-controlled crystallization, 3 civilizations, 3 organic additives, 3 different performance targets, all 3 the same underlying move, an organic polymer threaded through a calcium mineral, creating a composite the mineral alone could never be. And here is the part of Grok's synthesis that stopped the team. The solutions are not interchangeable. Volcanic ash does not grip stone the way starch lime lime does. Tannin scaffolds do not self-heal the way lime clasts do. Amylopectin does not build the shell microstructure that tannins template. Each tradition found not a general trick, but the specific compound for its specific enemy. Rome needed to survive water and found the chemistry that strengthens in water. The Maya needed to survive the jungle's assault on every surface and found the chemistry of fracture resistance. The Ming needed to survive the moving ground and found the chemistry of density, toughness, and grip in the one rice variety that carries the working molecule. 3 problems, 3 solutions, all correct. Whatever you want to call the process that produced those 3 answers, trial and error sustained across generations, systematic observation, inherited genius, it behaved each time exactly the way engineering behaves. Here is where this story breaks the pattern of the first 2 videos, because this one has a twist the others did not. For most of the 20th century, the wall was repaired with modern cement, and the results are the failing joints we have already seen. The 2010 paper landed in that context, and its authors did something unusual for a materials study. They recommended in print that sticky rice mortar be used for restoring the monuments it built, not as heritage theater, as the technically correct material, compatible with the old masonry in stiffness, in breathing, in movement, in chemistry, and in scattered heritage projects since it has begun to happen. Conservators restoring sections of historic Chinese city wall have boiled glutinous rice into their lime again, the original recipe touching the original stones for the first time in roughly a century. It is not the default. Most maintenance across 21,000 kilometers of wall still reaches for modern materials because the supply chains, the specifications, and the training all point that way, the same gravity that kept Roman ash out of modern concrete and Maya bark out of modern render. But the recipe is no longer only in the old joints. It is back in the buckets, in a few places, on purpose, which makes this the first story in our series where the ancient material is not simply buried under the modern one. Rome's formula waited 1,400 years for a laboratory. The Maya formula survives in a handful of village lime pits. The Chinese formula has started quietly to come home. 3 losses, 1 partial return. The scoreboard of remembering after 3 episodes reads, humanity 1, forgetting 2, and the game is still on. So here is where this lands. Ming Dynasty builders stirred cooked glutinous rice, the correct variety, prepared the correct way, into the mortar of nearly 9,000 kilometers of military architecture, producing an organic mineral composite dense enough to shed water, tough enough to hold cracked stone together, and tenacious enough that 6 centuries of earthquakes in one of the most violent seismic belts on Earth have not finished it off. The 2010 study named the molecule. The wall had been keeping the demonstration running the whole time, with the 20th century's cement repairs failing beside the original joints as a built-in control group. A kitchen ingredient specified by variety, prepared by recipe, procured at imperial scale over the objections of everyone who had to pay for it. That is not folklore. That is a specification written in the only language the tradition had, which happened to be the language of cooking. And the series now has its shape. 3 civilizations, 3 enemies, water, jungle, earthquake, 3 organic molecules threaded through the same mineral. Each one the right answer to its own question. Every episode so far has been about a recipe, something added to the lime. The next one is not, because there is a 4th answer to the earthquake problem from the other side of the world, walls that have ridden out centuries of seismic violence in Peru and Japan with no mortar in them at all, no lime, no rice, no binder of any kind, stones cut and fitted so precisely that when the ground moves, the wall moves with it, shuffles, dances, and settles back, while the buildings around it come down. Engineers have a name for what those walls do. The people who built them left no explanation of how they did it. That is the next video. When it goes up, you will want to have seen this one first. Subscribe now and turn on notifications. I'm Dr. James Mercer. The moment I have more, you'll be the first to know.